So we're learning about complex numbers today. The specifics of it is we're going to learn how to represent them using rectangular form. Then we're going to learn how to represent them using graphical form on the Argand diagram. And then we're going to learn how to work with them to transform them so we know their length, or the modulus, and their angle, also known as the argument. So complex numbers are typically represented as, let's say, consider, and we're going to use the letter Z in this instance, and we're going to go A plus I B, where this guy over here represents the real component. This guy over here represents the imaginary component. Where B is considered the imaginary component, of course, because we are looking such that I is equal to the square root of -1. So nothing new yet, is there? Now when we want to graph these, then what we find is that we graph them on what's called the Argand diagram. Argand diagram, where it's represented such that this horizontal number line is just our regular number line that we've been using since, I guess, year 1. And this vertical number line over here represents the imaginary component. So if we were going to represent this imaginary number Z, then what we might find is that this is our imaginary number Z represented on the Argand diagram. And we find that this guy over here is the imaginary component, so B. And let's just change this to orange here. Hence, this guy over here represents A. So what we find is that using the Argand diagram, we can represent a complex number in a graphical format. And it takes on the form very similar to one of the other topics we studied last year of vectors. So the really cool thing about complex numbers is we can use them to represent two-dimensional vectors, which gives us the opportunity to bring vectors into our regular number space. Or it's a tool for doing it. Alright, so suppose we have, let's go, example, simplify and graph. We're going to have Z, we'll have 3 plus 2i, and it's going to look like a W, and a lot of the times we call it W, but it's actually the Greek symbol omega. We're going to say omega equals, and we'll say 1 take, let's just say I, like that. Does that sound cool? Yeah. And we'll do A. We want to go, let's say Z plus omega. Sorting this out, all we need to do is we write them out in the form of their rectangular form here. I call it rectangular because it sort of goes across and up. So we go Z is 3 plus 2i plus and then you've got the omega, which is 1 minus I. We add the real components together, so it's 3 plus 1, and then we add the imaginary components, so 2 take 1 I. Simplify it out, this is going to be 4 plus I. Easy peasy lemon squeezy. Graphing this, we're going to have imaginary, real. Looking at this, we'd have 4. So 1, 2, 3, 4. Up by I, we get to here. So this is Z plus omega. Now the other way, oh sorry, not today boys. Alright, the other way of looking at it is you can add them like vectors. So we're going to have Z, which would be 3 across 2 up. So 3 across 2 up. So that would be that here.
And left one.
Left one. Oh, sorry, that's 4. 1, 2, 3, 1, 2. So there's your Z. And then 1 across, 1 down. That's your omega. So again, you can add them head to tail or tail to head, just like you do vectors, and the arithmetic works out the same as well. Sound reasonable?
Okay.
All right, next one. B. Suppose we have, where are we? 2Z multiplied by omega. Again, we're simply just going to do the multiplication as if we're expanding brackets. I guess settle or simplify the complex components and then collect the like terms. So this is going to turn into, subbing in for Z, 2, 3 plus 2i, times. This is going to be 1 minus I. Expanding out, 6 plus 4i. 1 take I. Expanding out again, this is going to be 6, take 6i, plus 4i, take 4i squared. Collecting the like terms, 6, take 2i, and then this one's going to become 4i squared becomes what, Jack?
Negative 4.
Just 4.
Just, yeah.
Yeah.
Negative, yeah. 4, I was thinking 4 squared.
Yeah. So this is 2i. So when you're multiplying together, if you get the I squared, you turn it back into it's a real component. Hence, graphing this, by graph I actually meant sketch, because it's not very accurate what I'm doing, but good enough. This is going to become, where are we, 2z omega. Simple stuff?
Yeah.
Okay, so that's all well and good. What happens if we do something a little trickier? What happens if we want to go C? What if we want to say Z divided by omega? Oops. What if we wanted to do that and simplify it? This would look like 3 plus 2i divided by 1 minus I. And of course we know to write it in its fractional form. But how do we do that? How do we simplify that? Do we remember? No. What you have to do is we have to rationalize the denominator here. We rationalize the denominator by taking the conjugate.
Yeah, that.
So we have to multiply by the conjugate. The conjugate in this case is going to be, actually, I'll just do it over here. We're going to do it as 1 minus I, 3 plus 2I. And the conjugate is just the opposite sign in this guy here. So it's going to be times by 1 plus I. Does that ring a bell?
Yep.
And it triggers the difference of two squares situation here. So downstairs, you're going to end up with 1 take I, 1 plus I. And upstairs it's going to be 3 plus 2I, 1 plus I. This is going to become 1 squared, take I squared. Yeah, that should be fine. And upstairs it's going to become 3 plus 3I plus 2I plus, let's say, yeah, that's a plus, plus 2I squared. Keeping on going, 1 plus 1 is 2. This is going to be minus 2, so that will be a 1 plus 5I. So if you wanted to, you could say it's a half plus 5 on 2I. Doable? So that's a really small Argand diagram, but I'm just going to run with it. Because why not? So this guy's going to be a half across and 2.5 up, so let's just say it's like that. So that would be Z over omega. Reasonable? And that's basically all of year 11 complex numbers right there. Except for two things that we'll do next. Any questions? All right, cool.